Let's begin with the intermediate value theorem. It says that if a function f is continuous on a closed interval from a to b, then for any value n sitting between f of a and f of b, there must exist some point c in that interval where f of c equals n. In plain words, a continuous function cannot skip over a value. It has to pass through every height in between. Next, the mean value theorem. If f is continuous on the closed interval from a to b and differentiable on the open interval from a to b, then there exists some point c in that open interval where the derivative of f at c equals the average rate of change of f over the whole interval. So somewhere in the middle, the instantaneous slope must match the overall slope. Now concavity. The second derivative tells us how the curve bends. Where the derivative of f prime or f double prime of x is greater than 0, the curve is concave up. Where f double prime of x is less than 0, the curve is concave down. A point where the concavity actually switches from one to the other is called an inflection point. Let's put this into practice by sketching f of x equals x to the fourth minus 4x cubed. First, we find the first derivative. F prime of x equals 4x cubed minus 12x squared. Factor that 4x cubed minus 12x squared equals 4x squared times the quantity x minus 3. Setting this equal to 0 gives critical points at x equals 0 and x equals 3. Now check the sign of f prime on each interval. For x less than 0, 4x squared is positive, but x minus 3 is negative, so f prime of x is negative there. For x between 0 and 3, 4x squared is still positive, and x minus 3 is still negative, so f prime of x remains negative across this whole middle interval too. For x greater than 3, both factors are positive, so f prime of x becomes positive. Notice that at x equals 0, the sign stayed negative on both sides, so there is no sign change, meaning x equals 0 is neither a maximum nor a minimum. But at x equals 3, the sign goes from negative to positive, which signals a local minimum, and plugging in gives f of 3 equals negative 27. Now for concavity, take the second derivative. F double prime of x equals 12x squared minus 24x, which factors as 12x times the quantity x minus 2. This is 0 at x equals 0 and x equals 2. Checking signs around these points confirms the concavity actually flips at both. At x equals 0, f double prime changes sign, giving f of 0 equals 0, and at x equals 2, it changes sign again, giving f of 2 equals negative 16. So we have genuine inflection points at x equals 0 and x equals 2. Here's the trick for locating inflection points reliably. First solve for where the second derivative equals 0, but never stop there. Always go back and check that the second derivative genuinely changes sign on either side of that point, because a 0 of the second derivative is not automatically an inflection point. This is exactly where learners trip up. They see f prime of x equals 0 and assume it must be a maximum or minimum, without checking whether the sign actually changes on either side. And separately, they see f double prime of x equals 0 and assume it must be an inflection point, again, without confirming a genuine change in concavity. Both shortcuts can lead you to the wrong conclusion, just like we saw with x equals 0 being a false alarm for the first derivative. A helpful teaching tip is to build one shared sign chart with 3 rows laid out across the same number line. The first derivative on top, the function's shape in the middle, and the second derivative on the bottom. Fill it in interval by interval, so every conclusion about increasing, decreasing, concave up, or concave down is clearly tied to the correct derivative, and no sign change gets missed or misattributed.